So this lecture is going to differ from the previous in several different ways. We're still not going to be diving into the circuit analysis theory yet. First, and I prepared this for my students in the circuit analysis class, I wanted to go over some practical engineering problems to get us used to thinking like an engineer, to get us used to thinking the way that we need to for these types of circuit analysis problems. Like in the previous lecture, I have included a YouTube reference. I'll include the link in the description, so I encourage you to check it out. Really cool video. So let's talk about a couple of these practical engineering problems. The first one that I formulated was a basic heart rate sensor. So we have a heart rate sensor that generates a voltage proportional to a patient's heartbeat, as defined below. We want to build a system that lights up an LED whenever the heart rate goes above 125 beats per minute. Let's assume that we cannot use any resistors for which the value is less than 1000 ohms. And so our main equation looks like this right here. We see that the voltage generated, which is proportional to the heart rate, is equal to the heart rate in beats per minute squared times 10 to the negative 6 volts over beats per minute squared. Again, I just made this equation up. It could correspond to some real-life sensor, but we're taking this at face value. Next, we want to choose an LED to use. Again, I want to emphasize, let's not focus too much on the theory here. Just take it all in, and again, I think there's a lot we can take away from this. So, to continue, we need to understand how an LED turns on and off, and we are going to talk about this in more detail later. Assume that we choose the LED that's shown below, right here. And it activates when the current through it is greater than 100 milliamps. And so what we see here is a diode. It has a current through it, which is ID, and a voltage across it, which is VD. And we see a common relationship, the exponential relationship for a diode, where the current through the diode is equal to 0.01 times e to the VD. And the threshold being 100 milliamps. So when this equation gets greater than 100 milliamps, the LED will light up. So as you can see, we need to find a way to make this right here work with this down here, where the VHR is going to be supplied as the VD down here. Now we need to calculate what the threshold values are going to be, because essentially we want the LED to light up when the beats per minute, when the heart rate goes above 125 beats per minute. So our two thresholds that we're working with are here, 125 beats per minute, and that should correspond to 100 milliamps. So let's work backward to determine what other thresholds exist. We see that the diode must be supplied with 2.3 volts in order to turn on the LED, and we get that number from this equation right here. All that I did was invert the exponential equation using natural log, and we see that if we input our threshold current of 100 milliamps and we use the 0.01, this is the coefficient from here, and we take the natural log, we've inverted this equation, and now we can calculate what voltage, if you were to stick it in right here, would generate 100 milliamps, and that value is 2.3026 volts. We see also that the heart rate sensor will generate a value of 0.0156 volts when it is experiencing or observing a heart rate of 125 beats per minute. So we need to figure out how to make these two values work together, 2.3 and 0.0156. We essentially want those to be the same. So what other components do we need? We need some component that is going to allow us to supply a voltage of 2.3026 volts to the LED when 0.0156 volts is generated by the heart sensor. So if we have the heart sensor, and that is generating 0.0156 volts, that corresponds to 125 beats per minute, we want that, and I'm going to put an X here, we want some magical component. We want that then to spit out 2.3026 volts, and that can then go to our LED. If we can make this component right here work, then 125 beats per minute will correspond to turning on the LED. So the component that can do that for us is an operational amplifier. And again, like I said, we're not really focusing on circuit theory here, so I'm going to go ahead and give you the component that we can use. So the transfer function for the component that we're going to use, which is an inverting op amp, the transfer function is given right here as well as right here. So what we see is that the gain between the input and the output, and so I can show you here that the input is going to be this 0.0156, and we want it to spit out the 2.3026. So the gain that we want is going to be equal to 2.3 over approximately 0.015. So knowing that that's the gain, we can figure out what resistance values will satisfy that. We need for this value to be equal to 1 plus RF over RG. And we have freedom to choose any values for RF and RG as long as neither are less than 1,000 ohms. Because if you remember, that's the threshold, that's the restraint or constraint we placed on the hardware above. So now we know that there's three components that are needed. I'm going to replace this X, I'm going to put here op amp, and with the gain that's already been determined. So let's put these components together to generate our potential design. All we're going to do here is connect the output of one element to the input of another, and we've already been given the transfer functions for these components. And this is the way that I'm going to represent it as a circuit. We see that there's three parts. We have the sensor, which I'm going to represent simply as a voltage source. Okay. Then we have our inverting amplifier, which is going to provide the gain and amplify the signal. And then we have the LED connected to the output of the amplifier. So we know what the desired threshold values are. We know what our circuit is going to look like. And we've been given the transfer functions, or the functions that describe their behavior, for all of the components. The last thing we need to do is figure out what resistance values will help us do this. So next step, we need to configure our op amp. Since we have two independent variables, both RF and RG, and only one equation, the problem is under-constrained. Under-constrained means that there's multiple solutions that will provide us the desired behavior. Now, just for the sake of ease, we're going to go ahead and define one of the values as being at the minimum of 1 kilo ohm. And since RG is in the denominator, we're going to go ahead and set that to be our 1 kilo ohm value. So what is this equation right here? This equation is essentially our transfer function, the same one from up here, except we've inverted it in order to solve for RF. And so you see here, RF is equal to RG, which we already know that's 1 kilo ohm, times our desired ratio of the voltage is -1. The V out is going to be 2.30 something, and the V in is going to be 0.015 something. And then we fill in the values. And so you can see here we filled in the values, and we calculate an answer, which is 146.6 kilo ohms. So we know RF equals 146K, and we know RG equals 1K. Now again, the point of this exercise is just to demonstrate the logic behind making these decisions. And so our design is complete. We know the configuration as well as the independent control variables. And we've already decided what components that we need. So we can go ahead and we're done, essentially. We have our finished design. Our design will look like this right here. We have our heart rate sensor. We have our amplifier with the appropriate values, RF and RG as decided. They're equal to 146K and 1K respectively. And everything else has already been defined. Now, we could test this in simulation. I'm not going to do that. Actually, I would encourage you to do that on your own. But this design would essentially allow us to build an alarm, an LED alarm, that would light up when the heart rate goes over 125 beats per minute. So a really, I'd say, succinct, interesting ECE circuit related problem that we've been able to solve without really learning any of the circuit theory yet. Now, for the YouTube videos, I'm not going to focus too much on the homeworks. I'm going to try to find a way to include the homeworks in the description. I haven't figured that out yet. But again, if you're interested, I encourage you to go ahead and simulate the circuit using LT-Spice. And I am going to prepare another lecture, which is going to talk about LT-Spice specifically. So another example. Let's take a look at a machine learning example. Now, this course does not cover machine learning, but it's one of my research areas. I have a lot of interest in it. So let's see if we can create a practical engineering problem about machine learning that we can solve. Again, take everything at face value here. I'm going to talk about neural networks, machine learning. If you don't have a background in this area, that's fine. So we're asked to design a circuit to implement a neural network that can be trained via machine learning. In other words, we want to create a circuit that can learn to predict some pattern of X being the input, we call it training input, and Y being the ideal sets of outputs, or the training outputs. Ideally, once trained, our circuit should be able to predict the value of Y from an input of X, and those value pairs could be from outside of our training data set. These data points could represent any pattern. It could be facial recognition. It could be trained to predict how a real complex physical system reacts. We decide to use a neural network structure like that below. You see down here. I'll show the full circuit in a second, or the full schematic in a second. And this is similar to how real neural networks are designed, with summed inputs supplied to some activation function. Our activation function is going to be simple and returns the summed inputs supplied to it. So here we have a really basic neural network. I'm going to spend just a quick minute explaining it. So we have 4 inputs, x1, x2, x3, and x4. Each one of them have their own corresponding weight, and they are supplied to our neuron, which has an activation function, and it essentially spits this out. It spits out W1 x1 plus W2 x2. You can see the pattern. It's the weight times the input. It's a weighted sum. So we have 1 neuron and 1 output. So how could we implement this in hardware? Again, taking our neural network design at face value. Fortunately, a closed-loop feedback op-amp configuration called the summing amplifier can fill this role. The transfer function for this type of op-amp is defined below, and we can make this circuit behave like the neural network above if we set our individual weights to the gain of those amplifiers, which is negative RF over the respective series resistance, which I'm going to call RK, for all of the inputs. So this is our transfer function right here. We see that we'll need essentially 5 different resistance values. We're going to set it up such that all of them use the same RF value, okay? But they have different R1, R2, R3, and R4 values, and by differing those, we can set up the individual W1, W2, W3, and W4 values. So let's take a look at what that circuit would look like. This is the schematic for an inverting summing op-amp. They all share the same RF value, although each one of the individual inputs have their own RK value, which is filled in or substituted into the denominator of their individual gains. And so that's essentially the implementation of the neural network above. The machine learning algorithm will be a little bit more difficult for us to explain. However, I have provided some MATLAB code to help us with the training process. The result will be 4, what we call synapse weights, 4 values which allow our neural network to predict the patterns reflected in the training data. The training is performed in several steps. Now, I'm going to say this part right here is a little bit of a tangent. It's not so applicable to circuits, but it's an area I really enjoy, so I figured it would be nice to throw a little bit of a machine learning twist into this class. So first we have to initialize our weights. We initialize the unknown weight values W in some manner. This may be done randomly or based on some pre-existing knowledge. Then we present the ideal training data subset, K. So we have training data that defines the ideal input and output relationships. Then we supply the ideal inputs to the untrained neural network and see what calculated value is generated. Finally, next, we quantify error. Now we have two outputs. We have the ideal value, which is known a priori, and we have the one that's generated by our neural network. So if we go back up here for a second and take a look at what's going on, let's see what would happen for a single piece of training data. We have a training data pair. Okay, we have an X ideal and we have a Y ideal. All right, we take that X ideal and we plug that in here, 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 and here. So the X is actually an array. It has 4 different values contained within it. We've initialized our resistances based on the initial weight values. That relationship was defined above. And this untrained network will spit out some X calculated value. Then we're going to look at the difference between that would be Y calculated, our Y calculated value, and we're going to compare that to the ideal value. And this right here is our delta Y. When that delta Y equals 0 for a large number of the training data samples, then we can consider our neural network to be trained. And so you can see here is that same error function defined. We flip the order of ideal and calculated. It doesn't really matter. We have to account for that in our machine learning algorithm anyway. Then what we do is update the synapse weights. Now this step is a bit complicated. We're going to use this error value to determine whether our answer is too high or too low, and by how much. Then we use this information to update the synapse weights, increase or decrease those values based on the magnitude and the sign of the error. So let's say, going back to this example right here, we end up with a Y calculated value that is 5, and we end up with an ideal value that is 2. The difference between those two tells us that our neural network is spitting out an answer that's too large. And so we may want to reduce the value of our synapse weights in order to bring that down. And so we do that in an iterative manner. Then lastly, we check for convergence. After that iteration, we check whether that error is dropped to 0 or not. It's highly unlikely that after one iteration it's going to do that. There are many ways to check for convergence. I already told you one, right, which is whether this equals 0 or not. Another way to check for convergence is to essentially see if the weight values from iteration to iteration change significantly. Normally those two coincide with one another. Once the error drops to 0, we begin to see that the synapse weights don't change a lot from iteration to iteration. Now, like I said, most likely after the first iteration, you won't have convergence, and so we begin the next iteration, and it keeps going on and on. So the thing that I wanted to focus on here was probably just the summing op-amp configuration, because again, this ties it back to circuits. We see that a summing op-amp configuration, which is something we are going to learn about in this course, is really powerful and can be used to emulate a really basic or a more complex, depending on how you configure it, neural network. And I think that's really interesting, especially for those of us that are still trying to, let's say, hone our interest in this topic. Here you can see the Matlab code that I've included for the training. I'm not going to go into too much depth on this, too much detail on this. If you're interested, I encourage you to, copy, download the code, try running it in MATLAB. Actually, I do want to say there's a really great Octave online for those of you that aren't familiar. This is a website that has a free MATLAB alternative. I mean, it's not as functional, it's not as capable as MATLAB, but it can definitely run a script like this. So once we run that, we can see that our final synapse weights are shown here. They're all negative, fortunately, because our circuit can only generate negative weights because it's an inverting op-amp. And so here we have a graph of the training process where along the x-axis we have the iteration and along the y-axis we have the error. And so you can see the error starts out relatively high when the network is untrained, meaning that the difference between the y ideal and the y calculated is high. As our training values, our trained synapse weights get better and better, the error drops lower and lower, and right around here we expect to see convergence. So again, the idea is not to focus on the machine learning aspect, but just to focus on how functional, how useful these types of circuits can be. And then we can calculate the resistance values for our summing amplifier circuit that represent the optimal synapse weights. So MATLAB told us that these are the optimal synapse weights. We have our existing transfer function from up above, and we can go ahead and plug in values or determine values of RF and R1 that generate those values. So for example, this ratio here needs to be negative 1.03. This ratio right here needs to be negative 2.51. This needs to be negative 5.01, and so on. And you can see I've shown some of these calculations. The first resistor, R1, should be 10K, and R2 should be 4K, and so on. So hopefully those of you who have some interest in machine learning and artificial neural networks, that provides a little bit of a preview of how you can use that sort of technology. Next, let's take a look at a power system example. Again, at face value, I'm going to give you all the models that you need. Let's assume that we have 3 generators connected to the same factory along 3 lines. The resistances of those lines are R1, R2, R3, and R4. The factory has an internal load resistance of 5 kiloohms, and to operate correctly, the factory needs to draw at least 112 kilowatts at all times. Now, the way that I've set this up, you cannot control the generator's power output, but we can control their current output within the following ranges. We see that generator 1 can give us between 0 and 5 amps. Generator 2 can give us between 0 and 15 amps, and generator 3 can give us between 0 and 5 amps. So this one is larger and has more capacity. We want to minimize the power loss for this system. So you can see here we have 3 different sources, which are just, again, current sources, I1, I2, and I3. And each one have their series resistances R1, R2, and R3. They come together at this junction, and then they flow into the factory, which has a resistance of 5 kiloohms. We want to minimize the power loss for this system, which is going to be defined by this equation right here. Again, I'm giving you the equation that you need in order to solve this. The loss is going to be dictated by the individual I squared R losses for each line. So I1 squared R1, I2 squared R2, I3 squared R3. How do we minimize this loss while maintaining the constraints up above? And the individual resistance values are given right here. R1 equals 3, R2 equals 2, and R3 equals 5. There are only a couple of expressions that we need, and they're both shown below. So we've already seen the lower one. The loss is equal to I1 squared R1 plus I2 squared R2 plus I3 squared R3. And the total power being consumed is going to be I1 plus I2 plus I3 times RL. Now, this is essentially dictated by what we call Ohm's law. We're going to learn about that a little bit later. And this one is derived from the expression S equals VI, and we make some substitutions in there, which I'm not going to show. Now, this is a homework problem. I'm going to go ahead and show the answer. Asking us, how do we solve for the optimal values of I1, I2, and I3? A good logical question. So, step 1. We want to minimize power loss. So why don't we look at the effect of each current on loss? We don't have to know anything about circuit analysis in order to apply this basic logic. So we're going to take the derivative of each one of the losses with respect to each one of the currents. And that's a derivation of the lower equation down here. Now what we end up with is 3 different derivatives. 2 times 3i1, 2 times 2i2, 2 times 5i3. These values are, this is the R1, this is the R2, this is the R3 value that we have. And what we see is that the greatest value is going to be, so over here we have a value of 6i1, we have 4i2, and we have 10i3. So we see that the greatest effect is going to be caused by current number 3, then next being current number 1, and the least effect is going to be current number 2. So we know the order in which we want to try to ramp these generators up. So since we know that I2 has the least effect on loss, meaning that by turning it up it's going to increase the loss by a lesser amount, let's try pushing I2 all the way up and see if we have enough power in order to supply our factory. So here we have our total PL, right? The total power consumed by the factory, with I1 being 0, I3 being 0. We're going to start off by just turning those two off and maxing out I2. So we have 15 amps times 5 kiloohms, and that gives us 75 kilowatts, which is less than what we need. Okay, we're asked to generate 112 kilowatts. So that means we're going to need some more power from somewhere. Let's try pushing it a little bit more, but we want to do it in a logical way. So we go back up and we see this one is already used up. We can't drive this one up any further. What is the next best option? We don't want to go with I3 because that has a really drastic effect on loss. So let's go ahead and ramp up I1 next, the first generator. So what we do is we leave I2 pushed all the way up, and now we push I1 up as well to 5. I3, you'll see here, is still at 0. So we have 5 amps plus 15 amps times 5,000. That's 20 amps times 5,000. That gives us 100 kilowatts, which is still less than the 112 kilowatts that we needed. So we know that we're going to need some I3. And we can simply just solve algebraically to determine what that value should be. We'll take this equation right here. Okay, there's only one unknown left. We know what PL is. This has to be 112 kilowatts. We know what I1 is. It's 5. We know I2 is 15. We know RL is 5. And now we just need to figure out what this value is. So we invert this equation and generate that which is shown here. We substitute in the values that we know. Again, 112 kilowatts, 5,000 ohms, our 5 amps, our 15 amps, and we end up with I3 needing to generate 2.4 amps. And that's good because it's less than our maximum. Now, if this were asking I3 to give us 6 amps, then what would that mean? There would be no physically realizable or feasible solution to this problem. But that's not the case, right? It's lower than the threshold. So we have our answer. I didn't check it, but if you plug this value back in, if you plug in a value of 2.4 amps right here, we should end up with an output of 112 kilowatts. So that's our answer. Now all we have to do is figure out what is the loss. We already have that equation. You remember that was P loss equals I1 squared R1 plus ... We have our optimal current values, 5 amps, 15 amps, 2.4 amps, and what we see is that the minimum loss that we can generate is 553.8 watts. This is a nice linear problem that we can solve without having to know a lot about circuit analysis. And that essentially concludes this lecture. Again, the goal here was really just to get you thinking logically and get you used to using models that are presented to you mathematically in a logical way. Because for most of this class, that is how information is going to be presented to you.